Welcome. Hello, welcome to the APS Journal Club. My name's Matt Eager. I'm the managing editor of Physical Review Applied, and I'll be your host today. We at APS have established our Journal Club series of talks to highlight some of the very interesting research that appears in our various journals and to provide a venue for authors, particularly early career researchers, to discuss their work interactively with the community in a relaxed setting. If only I could give you coffee and donuts to go along with it, but not this year, guys. Today's talk will be on a PR Applied paper from January that we chose as an editor's suggestion. Hardware-aware in situ learning based on stochastic magnetic tunnel junctions by Jan Kaiser and his colleagues at Purdue, Tohoku University, and UC Santa Barbara. Jan will be our presenter, and our moderator will be Matthew Daniels of NIST in Gaithersburg. Before we get started, some brief announcements. Only if I could, there we go. PRX Energy is our newest member of the Physical Review family. In much the same mold as PRX Quantum, PRX Energy is a high-impact, multidisciplinary journal spanning many research communities and subjects, all centered on energy research and technology. This is a fully open access journal, and for the rest of this year, we're waiving publication charges. PRX Energy is open for business right now and just published its first papers last week, so spread the word. Next time at Journal Club, come hear about a recent PRL paper on dark matter detection from Afik, Moore, and Carney, and moderated by Raphael Lang. That'll be next Monday, April 25th at noon on the East Coast of the USA. Zoom etiquette. Please be sure to stay muted unless the moderator calls on you. Please use your real name, which you can set by right-clicking on your handle in the participants list. We'll hold questions until after the talk, but feel free to enter them in the chat window as they occur to you, or just raise your virtual hand during the Q&A portion. All right, without further ado, I'll pass the mic to our moderator, Matthew Daniels, who will tell us a little bit about himself and the context of the work at hand. Dr. Daniels?
Yeah, thanks, Matt. So yeah, my name is Matthew Daniels. I did my PhD work at Carnegie Mellon under Di Zhao, which was all about variable phase physics and spintronics, but I took a hard right turn for my postdoc and moved into neuromorphic computing. And there's a lot of cool stuff that we've been playing with there at NIST, like temporal computing and low rank computing. But one of my first projects as a postdoc was actually on stochastic computing using these superparametric tunnel junctions that Jan will be talking about. So I think that's a really cool field. You know, it's very relevant because these MTJs are just such mature devices compared to some of the other novel devices we tend to be interested in condensed matter. So I think this is going to be a very impactful and relevant topic. And I'm really excited to hear what Jan has to say about their work looking at the hardware-aware learning of these systems rather than just sort of translating in parameters learned from a computer. So with that, Jan, I'll pass it to you and let you get started.
Let me stop sharing. The floor is yours, but unmute.
Yeah, thank you very much, Matthew, and thank you very much for the invitation. So let me get started. So you can see now, right? What? Sorry, why does it? Okay, so Today we'll be talking about this hardware or in situ learning based on stochastic magnetic tunnel junctions. And before I get on, and first I will give you like an overview of this probabilistic computing that we are working on. There's this, what you might call recent developments in physics-inspired computing. And the overall idea is to map a problem to a physical system and then improve efficiency and performance and compared to general purpose processors like CPUs or GPUs. And on the classical side, there are, for example, these Ising machines, which are digital or oscillator based. There's also some optical oscillators that use it, and then there's also this field of quantum computing, where which also use this idea of mapping something to a physical system to improve the overall performance. Today I will be talking about one field, which is probabilistic computing with Pbits, and let me tell you about what we mean with Pbits. We are familiar with the concept of a bit that is either 0 or 1, which is used in all of digital computing and can be represented by stable magnets, and it is used to power the CPUs, GPUs, or FPGAs. Then on the other side, there is this field of quantum computing, where each qubit is a superposition of 0 and 1, where it can be represented by a single spin. What we'll be talking about is this Pbits, which fluctuate between 0 and 1, and are basically domain-specific computing based on these unstable magnets. And compared to the digital field, an advantage is that it is usually expensive to simulate randomness, whereas in probabilistic computing, this randomness comes for free. And an advantage compared to quantum computing is that it does not need these cryogenic temperatures. So how do we define a Pbit? A Pbit is basically a tunable random number generator or a binary stochastic neuron, and it has this continuous input and a binary output that can be described by this transfer function on the top right, where if you apply like an input of 0, then you get fluctuations that are 50-50, and if you then apply a positive bias, it goes more towards 1, but it still has some fluctuations. But if you apply a very large bias, then it becomes a deterministic one. And if you apply a negative bias, the opposite happens. And the overall average, if you look at the average of this Pbit characteristic, you get this 10H. So this magnetic tunnel junctions can be used to get this random number, basically get this stochasticity into this Pbit or binary stochastic neuron. And magnetic tunnel junction is a 3-layer device that has a fixed layer, tunnel barrier, and a free layer. And usually it is used for memory. And in this case, the free layer, as well as the fixed layer, is a ferromagnet with a large energy barrier that makes it stable, so that the magnetic orientation will be the same for years or longer. And depending on the orientation of the free layer compared to the fixed layer, the overall resistance based on the magnetic resistance effect will be different. So if the orientation is in the anti-parallel state, the resistance will be larger than if it is in the parallel state. And what you can now do to actually make it a stochastic magnetic tunnel junction and make it fluctuating is if you change this stable ferromagnet in the free layer and make it unstable, make it a low barrier magnet. So now this thermal noise can actually change the orientation. And what happens is that if you look at the overall time trace of the resistance, it can actually change very fast, and it has been shown theoretically and also now in some experiments that this fluctuations can be on a nanosecond, nanoseconds. So how do you now use this magnetic tunnel junction to make a Pbit out of it? This happens by using this 1T, 1 MTJ cell that's also used in MRAM technology, but with two crucial differences. One is that the free layer of the MTJ is now a low barrier magnet. And then there's also this inverter that thresholds the voltage. And what happens is that you have this fluctuating resistor. This is the stochastic MTJ, and then a fixed control resistor that can change this resistance compared to depending on this gate voltage. And if you, for example, apply a very large voltage or a large voltage, what happens is that the resistance of the transistor becomes smaller than the resistance of the stochastic MTJ, and what you get is that you get this deterministic 1 if you apply and the opposite happens if you apply a low voltage. But the interesting thing that happens if you actually apply a voltage that is that makes the resistance of the transistor comparable to the resistance of the MTJ, and what happens then is that you actually get this fluctuations, and the overall transfer characteristics can then be described by this equation number 1 again with this tan h and the random number. But now everything has physical quantities voltages, and the advantage of doing that is that compared to digital circuits like linear feedback shift resistors, you have no pseudo-random numbers, you save energy, and you save a lot of area because it's just one MTJ and 3 transistors. So this three transistor, 1 MTJ device can be seen as a compact and efficient hardware accelerator of equation 1. So how do you build a probabilistic computer with it? What you need to do is you need to connect them, and what happens is that you have a synapse that takes out these digital outputs, computes a function, and sends it back in. And this overall idea is inspired by this paper from Feynman from 1982, that if you want to simulate the probabilistic nature, you have to build a computer that is probabilistic by itself. And one way to design this computer is to actually use this Ising model, where you will use an energy function that where the states of the Pbits are basically spins and can be described by this energy function here. And depending on the state of this connection matrix W and the biases H, the Pbits will then be in a state that can be described by a Boltzmann distribution, where the lower the energy is, the higher is the probability of being in that state. And what is interesting about this is that the standard synapse equation is then a standard, like just a linear sum between the neighbors, the connected spins or connected Pbits, and so the Pbit can naturally represent such an Ising machine. And this paper from this Nature paper from 2019 did something like that, where there were eight Pbits in the lab where the synapse was designed to do factorization. One thing that we then wanted to look at is if there's a way to learn the system and basically learn this W depending on some functionality that you want to map to the system. And this was important because usually with this emerging spintronic hardware, there are some variability concerns, and even for some of these experiments, it was necessary to do some per hand tuning to make sure that the Pbit response is as expected. So one question was, how can you actually you could use a machine learning system to counter these variations? And these non-idealities or device-to-device variations can look differently. For example, it could be that different Pbits have a different 50-50 point. So here, this is now the average Pbit response, because the Pbit will always be in a bipolar state, but the average Pbit can look different. And here, what happens is that actually the 50-50 point is shifted. And what can also happen is that you could actually not have a 10H or have a very different looking transfer characteristic. And the question that we were looking at is, can you use some learning to make sure that the system still works? And this can be done by the by using some of the Boltzmann machine learning techniques. And in this example, we were looking at a full adder where you have this truth table with 8 lines, where ideally you want to have every line of the truth table equally represented. So in this case, for example, 0 should give you a 0. If you have a 1, it should give you a 1. And usually you want this to be, in this case, 1/8 probability of all these 8 states, depending on all the 32 different states that a 5 Pbit system could be in. Well, you have the 3 inputs A, B, C in, and the 2 outputs, the sum and the C out. And the system can be described by a Boltzmann distribution, where you have this energy function. And now the question is, how can you actually change the W matrix so that the Pbits follow a full adder distribution? And this can be done using this well-known Boltzmann machine learning algorithm, where you have weight or the weight matrix at time t, and if you want to update them, you have to look at your data distribution, which are these V1s and V2s from the truth table. So you look at these average correlations, and then you compare them to how your Pbits fluctuate based on the weights at time t. And then there's also a regularization parameter that makes sure that the learning converges. And then, general, an advantage of this learning rule is that it just requires local correlation. You just need to look at the correlation ij to update wij. It has, because of that, it is biologically plausible, and it has the advantage that you can naturally get this MIJ model, because usually if you have very large Pbits, there could be 2 to the n configurations, and sampling using this Pbit approach is helpful. So what we then did is that we actually mapped this function to a RC array, so that you can use this discrete function, the discrete formula, and map it to a time continuous version where every point in this is now becomes a voltage, and it can be shown that basically this learning time constant epsilon now becomes the RC constant, and the voltage across the capacitor is now represents this weight matrix Wij. So in summary, what we added was basically this learning rule. You have this Pbits, you have a synapse. Now there's a learning rule that dictates how the Pbits should fluctuate. And this is the overall learning circuit that we've built, where you have this neuron, so the Pbits. You have a synapse that is a microcontroller and a DAC. Then you use this XNOR to get this correlation between Pbits and send it to a RC array, and then you can use these voltages that are connected to the RC array to feed in the data. And this is how this looked on the lab. On the right, you can see the stochastic MTJs together with transistors and this RC array. And in this paper, we had 2 different different ways of implementing it. One was was using actual MTJs, which had some non-ideal characteristics, and then we also used the MUX model, where we implemented two parallel resistors that were with a MUX multiplexer that, depending on the input voltage, would switch between this RP and RAP. This is kind of a compact way of emulating an MTJ. And with this ideal MTJ, we got this we got this response on the top right, and with this non-ideal MTJ, we got some of these this non-ideal characteristics on the bottom right. And what we saw was that, independent of what MTJ we used, we still were able to learn the same functionality, this full adder functionality, you can see at the start, the distribution does not look at all as wanted, but after the learning was performed, you can see that this 8 peaks of the full adder are shown. And one way of looking at that is to look at this KL divergence that compares this experimental with the ideal distribution. And you can see that both devices showed similar learning performance, while also showing this 8 wanted peaks, which shows us that there's some way of countering this variations of the non-ideal Pbit characteristics. And one way to see this also is if you actually look at the weights that were learned and measure these voltages across a capacitor, and you can see that these 2 different devices also learn different weights. So there's this ideal and there's non-ideal weight voltages, and they are different because they are basically learned just for this distinct Pbit response. And another thing we looked at was what would actually happen if you extract these Pbits now, this weights now, and put them on the Boltzmann distribution. And what we saw was that the almost ideal MTJs that just had a bias shift were also on a digital computer. If you just extract the weights and look at the Boltzmann distribution, they would also give you this right full adder distribution with the 8 peaks. However, this non-ideal MTJ weights did not work because they were just learned for this for the Pbit response on the bottom right. Yeah, one thing we also did in this paper was that we looked at, so this was all the full adder. So another thing we looked at was also at the different functionalities, for example, AND gates or XOR gates. And you can see that here also the right distribution was learned. So on the left, you can see the AND gate, and on the right, you can see an XOR gate that also was learning the right the right distribution based on the AND gate and the XOR gate truth table. Yeah, with that, I want to summarize. So in this paper, we've shown a proof of concept experiment to learn probability distributions in hardware. What we've seen is that device-to-device variations can be countered by learning this hardware-aware weights, and we think that the system-level variation tolerance could allow this scalable MTJ-based P computers to address many probabilistic tasks while having a large footprint reduction compared to this conventional implementation that would, for example, include this linear feedback shift registers. And going forward, this Pbit hardware could be combined with this large capacitive crossbar or even a memoristic crossbar, and should help to do some fast and efficient learning based on this Boltzmann machine. Yeah, with that, I would like to thank you for your attention, and yeah, I'll be happy to answer questions.
All right, it's great talk, Jan. So if people want to applaud, you may briefly unmute your mics or use the little Zoom clap button. It was a great talk, and feel free to raise your hand if you want to ask a question. I can call on you, or put it in the chat if you don't want to speak out loud, I guess. So I will wait for hands to come in, raised hands. In the meantime, I'll start with a question, which is the nature of the non-idealities that you're studying here, right? So you pointed out that there's the bias shift and also the non-sigmoidal nature of the probabilistic response, right?
All right.
So one question I had, if you look at the bias shift, how much bias shift were you looking at in this study? And do you have sort of thoughts on how far the bias can shift and still being able to train around them? Is that something that, yeah, I think you answered my question. How far can you train around bias shift?
Sure, that's a good question. In general, the bias shift was like relatively easy to fix because there's a parameter for it. So there is this. I mean, in the model, in the Ising model, you have this H parameter, which is kind of directly let me show this HI here, which is directly doing this bias. So the only question would be, okay, what is the largest weight that, or the largest weight that you could store on your capacitor, which is kind of based on the technology. If you have like doing it with 5 volts, you cannot, at some point there will be a limit, but the bias I think could be like 3 volts, or could be very large. If so, the question would more be like, what is the largest weight that you can store and then this would also answer the question how much bias shift you can counter.
Okay, that makes sense. Great. So let's see. Again, if you have any questions, feel free to raise your hand in the Zoom interface. I don't see any yet, but that's fine because it gives me opportunities to just keep asking questions. Yeah, actually, I really enjoyed the paper. I did go into it, and oh, hold on a second. Here's a question in the chat. I'll ask that before I take up all the bandwidth here. So Martin Rodriguez Vega asks, in general, what tasks would you expect a Pbit to be better suited to than a bit or a qubit? Maybe that's one question. And then he asks another question. What about integrations of the 3 technologies together? Or maybe, 2 of the technologies together or something.
Sure. So for the first question, there are these many stochastic algorithms that can make use of Pbits. This, for example, is stochastic optimization, where you have these different NP-hard problems, for example, like the traveling salesman problem. There are like many algorithms that use stochasticity, and they can be used to where Pbit can help. And for example, one way is also to we have talked about this full adder. One thing that you can actually do that you cannot do with a bit or a deterministic bit would be to actually run this full adder in reverse invertible, where you could clamp the outputs and see what the input is. So this is also something that cannot be done on a deterministic computer. And then the other question was about integration of these 3 different equations. So yeah, we have been focused on the Pbit, on this equation number 1. In this experiments, what we've done, we've used the microcontroller and this RC array on a PCB. But yeah, moving forward, there has to be some way of not using a microcontroller. There could be, for example, crossbars that can be integrated with the Pbit technology.
Yeah, as this whole zoo of different technologies keeps evolving in parallel, I think it'll be fun to see what happens when you clash them together, right?
Right.
All right, so I'm getting some other questions now, so I'm going to call on people in order as best I can. And I think, Ibrahim, if you want to unmute yourself and ask your question.
Okay, thank you very much for the talk, which I really appreciate the talk. Please, my question is that my area of research is computational material science, particularly DFT, which I normally use like spintronics in determining the electronic properties of material. Is it possible that I could be able to use this Pbit to determine such kind of in electronic properties? I'm using DFT, so I just want to know, that is density functional theory. I wanted to know that if I could be able to use some of these techniques using machine learning to operate in my field of study.
Yeah, that is a good question. I'm not aware. I don't think we have looked at it, and if Professor Kamsari or anybody wants to chime in, I'm not sure if there's any specific, but I think we could look into that. We have not looked at that so far, but it could well be that Pbits could help there as well.
Okay. Okay, thank you.
Okay, so I think Tanner, if you want to unmute.
Hi, can you hear me?
Sure. Yes.
So I have a sort of general question. I'm generally aware of all these sort of different models of computing, or not models, kinds of computing. There's probabilistic, which is what you're talking about here, and then there's the classical and also quantum computing. And I know that each of these have, there's like attempts to make physical devices that can perform these kinds of computing. Is there just like a review article or some other place where I can learn more about this sort of area of physics of trying to design things that can do these different kinds of computing?
Sure. Yes. So there are many review articles. I could send you many, but I think they're also cited in the paper. There are many different like based on Ising machines, but also on probabilistic computing. We've written review articles that talk about especially this this Feynman-inspired probabilistic computing. Yes.
Okay, yeah, I'll look at the paper. Thank you.
Okay, so Thomas asked a question in the chat. I think it's a very good question. What is the scaling law in the combination of Pbits when taking realistic peripheral circuits into account?
Scaling law in meaning if you want to build a large probabilistic computer, is that right?
Yeah, I'm tempted to extrapolate this question with my own question, but Thomas, if you want to clarify it all, feel free to write more in the chat or ask. But that's what he asked. So what is the scaling law in the combination of Pbits when taking realistic peripheral circuits into account? And I assume that part of what that means is, presumably there are fundamental limitations in the timing and connectivity of CMOS itself. And maybe how does that influence the scalability of Pbits beyond n equals 4?
Yeah, maybe I can chime in. So there are other ways of having probabilistic computing, for example, like with vanadium oxide or something, which are based on phase recognition. And this seems to be very hard to implement into larger realizations. So the papers which document this are then talking about 6 vanadium oxide devices. But so I'm interested in what are your expectations in the scaling of such a probabilistic computer with STT or SOT MRAM Pbit devices.
Right. So I mean, just on the memory device, there have already been like megabytes, gigabytes of MRAM memory. So the way we are working on the probabilistic computer is that the connections will be electrical, but of course at some point there will be like the connectivity. If you have like 500,000 Pbits that would be connected all to all, and at some point just because of the routing, it will be hard to do that. So as long as there's some sparsity in this W matrix in the connection between Pbits, the scaling should be possible. But we have not looked at it in a much into we've done this proof of concept. We have looked at some pre-programmable gate array emulations of this, but we have not looked at what it would look at as an ASIC level. But yeah, my guess is that at some point there has to be some limited connectivity to be able to scale it up, because otherwise the routing between these Pbits will be difficult.
Okay, thank you.
All right, so let people chew on that and hopefully raise some more hands with questions. While we're on the topic of scaling, I kind of had more of an algorithmic question. You look at these plots like in the bottom right corner of your screen right now, and a lot of the probabilities that sort of correspond to the undesired outputs are very small, but not quite 0. And I kind of have 2 joint questions. One is, as you scale, presumably as you scale bits, the space of the XY plane there is going to grow exponentially. So how do the accumulation of exponentially many non-zero probabilities, is that problematic, or does the relative probability of the peaks sort of save you in some way from having to sample more than you would expect? And I guess, yeah, let me start with that question. So how do these probabilities scale as you go to larger n? And is there a way to actually make the undesired probabilities go exactly to zero? Is that merely an issue of algorithmic instability or learning rate or device variability? Or is there really a way to get it to zero probability?
That's a good question. I think from an algorithmic perspective, it is not really the question. I mean, the good thing about this Pbit system or this Boltzmann distribution is that you kind of also in this experiment you want to get the high probability states, right? You don't really care about the low probability states, and usually what the sampling does is that it will just stay or will just sample from the large probability distribution, and it doesn't really matter how much non-zero states are there. Sometimes what is important can be like if you have different regions that are high probability, and you kind of want to make sure that you actually find your global minima. For example, in this factorization, you want to find your global minima, but there are local minima in between, and to be able to for the Pbits to actually go out of the local minima and go to the global minima, you want to have some low probability to the states in between, so that there's actually possibility to go there. And there are like ways of annealing. Annealing is one way of we actually change this Boltzmann temperature to allow going to this low probability states. This would be my response. But yeah, maybe if there's somebody else who wants to chime in, that would also work. But I think that's how hope I answered your question.
Yeah, I mean, I guess the first part of my question there was, as the x-axis and y-axis here gets exponentially many bins, if you only want one of them to be the output, are you going to be overwhelmed by exponentially many small probabilities? And it sounds like the answer is maybe no.
Right. You kind of want to give the computer a path to actually go to the largest probability, but once you're there, you don't really care about about all the others.
Okay. Yeah, one thing somebody, I guess Thomas was asking about scaling, and I'm kind of asking about scaling a little bit. And one thing that was in the supplementary material paper, I'm not sure how many people went back and read the supplement, but you guys did this neat calculation, basically training a Boltzmann machine to learn MNIST. And I guess one question I had about that was, it's maybe not even a question. I just want to give you my thought and maybe see if you have anything interesting to say about your MNIST calculations. Because if you train a single layer perceptron, so that's a one layer neural network, which doesn't have that much expressive power compared to deep learning systems. If you train a one layer perceptron on MNIST, you tend to get like 87 to 89% accuracy. I know that for you guys, you got 81% accuracy. And I'm wondering, what really is the difference? Seems to me that if you just get rid of bidirectionality and cut a few of the connections, or a restricted Boltzmann machine, or a full Boltzmann machine like you have, becomes a perceptron. So is there a meaningful difference there? Is it possible to look at these things quasi through this neural network lens, or is there really something fundamentally different going on?
Yes, I think one difference is that it's fully visible, and there are like these connections that are between learned neurons, and there's just one output, and I think that makes usually you would have to have more of an output layer, whereas here everything was connected in between. So I think the overall Boltzmann machine architecture was not designed to do MNIST, and this is why we had a relatively low accuracy, and I'm pretty sure that this was independent of any hardware. I'm not. I think at some point I checked to make sure that there is no way to actually get much better than this 81%, at least for this particular network.
Yeah, I looked around and tried to find other people who had done it with non-restricted Boltzmann machines, and there isn't a lot of that out there. You guys are maybe some of the first.
It's usually you do like this restricted Boltzmann machine.
Yeah, exactly.
And usually you also do I think add some more hidden units, but in this case, because the experiment was fully unrestricted and fully visible, that's also what we did for the supplemental information.
Oh, muted myself. As a reminder, if you have any questions, you can raise your hand in the Zoom interface or just ask them in the chat. But let's see. One of the other things, and this maybe comes back a little bit to the scaling question, but you mentioned earlier the idea of some other systems like integrating memristor crossbars and stuff like that, and you could start to imagine taking over parts of the interaction calculation, using non-digital methods. Are there prospects for removing that digital intermediary altogether? Do you think that's something that is, I don't want to use the word possible, but is that reasonable or even a productive way to go? Or will you always want to have sort of this some equivalent to the microcontroller that you guys have in this experiment?
Right. So in this case, the Pbit is also, it has a continuous input, but a digital output. So in that sense, it also makes sense to have some digital part to have like a mixed signal circuit. Even for the weight update, also on the Boltzmann machine side, there is some discrete way, or every update is kind of discrete, because the correlation can either be 1 or -1. So in that sense, in this circuit, there is definitely some analog voltages. There's at the gate, but there's definitely also some digital part. So I think what will be important is combine both. But I wouldn't say that, at least in this circuit, that there is one way to go fully analog, or it is desirable to go full analog here.
Okay, so with analog, especially, I just have memristors in my mind because you were talking about them earlier, but you mentioned them. But memristors have some conductance noise, and of course, there's lots of noise sources in analog systems. So, are there concerns with as you inject noise into sort of analog communication in these systems? Is that something that is of concern for convergence when you start to scale, or is that something that you expect to wash out and sort of just become part of the stochastic calculation?
From what I've seen, it seems that this noise and weights or noise in general doesn't seem to affect this too much. So this was one advantage of this. It's one of the advantages of this circuit, so that you can kind of, as long as there is no, as long as the noise has like a clear mean, or is not varying very fast over time, it seems that the circuit can just adjust accordingly and still have the right functionality.
That makes sense. I guess that's not another non-ideality you're training around.
Right.
So Matt Eager put a question in the chat. Do you want to ask it out loud, Matt, or do you want me to read it? Either way.
It sort of is along the lines of what you just addressed. I don't think that your magnetic tunnel junctions are actually limiting the performance of the hardware here, but what if you did get much better MTJs suddenly? Would you realize better performance in this, or maybe it would simply not take as long to achieve the same level of training? What do you think?
Yes, that's a very good question. So in this case, the learning was very slow, and one reason was that the stochastic MTJs fluctuate in the order of 10 to 100 milliseconds. But what I've I think mentioned very shortly at the beginning is that there have been recently in last year have been 2 experiments that showed that actually these stochastic MTJs can fluctuate at nanoseconds. So in principle, all these time scales could go up by multiple orders, so that they're a lot faster just because the SMTJs are a lot better and have faster fluctuations.
Okay, so Ahmad has a question in the chat. He asks, is it possible to increase memory by using possible paths and modes? I'm not sure, Ahmad, I'm not sure exactly what that means. I don't know, Jan, if you have an answer to that, but Ahmad, you can also unmute yourself if you want to clarify. If not, Jan, I'll let you interpret that. Is it possible to increase memory by using possible paths and modes?
Yeah, I'm not sure if I understand it either. Maybe some of the co-authors. Yeah, I'm not sure. I'm sorry.
Okay, well, Ahmad, if you're able to clarify that in the chat, I think that sounds like an interesting question. So hopefully we can get back to that. One thing that is maybe a more algorithmic question again. I was again looking at the supplement at the end of the paper, and you did a really nice comparison of and or and XOR training, and the KL divergence of XOR did not get nearly as low as and or, which isn't surprising. We know XOR is a harder problem. So, but it made me wonder, what are sort of the different difficulty classes of problems, and as you scale this technology up, what are the problems of interest, and are there sort of different degrees of hardness of problems that you want to solve, and will those different degrees of hardness require maybe different levels of connectivity or of MTJ performance or other, what's the problematic, what's the domain specific considerations that you're interested for in problems as you scale up?
Right. So regarding the Kyle divergence, one important point is that there's this temperature parameter that defines, which kind of is defines how strong each Pbits is coupled, and and this is why the Kyle divergence doesn't really. I don't think you can compare much between different problems. They kind of tell you how the learning develops over time, but it's not that you can say, okay, if the Kyle divergence is larger for XOR, it means that the learning is harder than for the AND gate, because there are different parameters in there. So what is true is that ideally the Kyle divergence would be 0 if you get the truth table correctly. But there is also this point that you mentioned, is that you kind of sometimes it could be that you actually want to be in some intermediate state to be able to go from one line of the truth table to the other. So in this systems you don't actually want to be completely 0 with the Kyle divergence. Can you repeat I think there was a second part of the question.
No, I think that answers my question. That's a great response.
Okay.
I didn't even really understand that about the different KL divergence metrics. Now, Thomas has a question. Are there any clear mapping algorithms for larger problem sets like QUBO?
QUBO? Sorry, can you?
Yeah, QUBO, QUBO. to be honest, I can't off the top of my head remember what that
Oh,
acronym was.
cool. I got
Yeah.
it.
But yeah, he's asking if there are any mapping algorithms. So presumably being able to solve these problems using this type of Pbit hardware.
Right. So there's a paper by Lucas that shows how you can there are these many NP hard problems that you can actually map to this cubo formulation, where you have a problem instance, for example, finding a route like the closest route between different cities, and there are ways to mapping them to this Ising model using this Wij formalism. And in principle, there is no limit to this mapping. This works usually. It's just that there are different scaling laws depending on how many cities you need, how many Pbits you need to implement cities in general. But this is definitely possible, and there is no no limit of how large this mapping, how the mapping could work.
All right, hopefully that answered your question, Thomas. We have a couple minutes left, so if people have more questions, please feel free to submit them, or even better, raise your hand. Let's see, I had another question about, what was it? So one thing that you mentioned in the paper, at least, I don't remember if you talked about it in the talk, was that ideally you have this op-amp in these neurons, but it would be nice if you could replace that with, say, a CMOS inverter, right, or a buffer, a couple transistors, right? And from at least sort of the experimental work that we've done with SMTJs, I know that with 2-level MTJs, you tend to get some sort of level noise around the P and AP states. I just sort of wonder, as you imagine scaling to a CMOS implementation of this, how many layers of inverters do you think you need? And are there ways to improve the MTJs themselves that would eliminate the need for extra CMOS there? Like, what are the material challenges in getting cleaner sort of telegraph noise signals? Or is that noise that I'm thinking about not even a problem, and a single CMOS buffer would do perfectly fine? Maybe I'm misreading the problem.
Right. So we have done some SPICE simulations where we had a magnetic tunnel junction model, stochastic magnetic tunnel junction, and these models use latest technology, and they're actually and I can actually show this, and there we just need actually one inverter with this with this inverter here is not an op-amp, it is just an inverter with 2 CMOS transistors, and there you get this output, and this is shown in this paper on top. So this seemed to be good enough. You can see that there is some non-ideal voltages here where it's not completely 0.4 volts at some input voltage, but it is good enough for the applications that we've looked at. And these are our circuit simulation with just these 3 transistors and 1 stochastic MTJ. The reason why in this paper we had to use an op-amp as well was that there were some need for this reference voltage to actually do not just not threshold exactly in between VDD half, because there were some variability in the resistance of the stochastic MTJ and the transistor. So this was helpful here, but it was not that it was there because because of the transistor. It had like different reasons why we used an op-amp here.
Okay, great. Let's see. So who was it? Somebody asked earlier about review articles, and I actually came across, I don't know if this makes you nervous or if you're happy for me to plug it, I saw you and Professor Dada had a recent review article at the end of last year on arXiv at least. So I was kind of looking through that a little bit, and I don't want to dig into it too much, but in it, it's probabilistic computing with Pbits. In it, you talk about a lot of different applications, and I just wonder if there's any particular class applications that you're most excited about for any particular reason as sort of the next step. Going beyond these sort of 4 to 8 Pbit systems and these simple demonstrations, where do you think is the next place to look for, a non-trivial but interesting experimental demonstration?
Yeah, this is a very good question. So one thing that we have looked on recently was also ways of going beyond this Ising model, so that you, because there are some, let me show. So there are some ways of also using Pbits in a way that they are not just connected using this Ising model, but also other possibilities. So for example, using like general Monte Carlo and Markov chain Monte Carlo problems and algorithms, and using that there's some way of doing Bayesian reasoning, and there's also like a large class of combinatorial optimization. And one thing we looked at, this was also it's also an abstract problem, but yeah, we think that there are many more problems in also in biology or in cryptography where you can actually use Pbits and not just use the Ising model to represent them. And I think this was one of the points that we made in this recent review article.
So we have time for maybe just one more question, and there's more than one question in the chat actually. So feel free to contact. I assume feel free to contact the authors afterward.
Yeah, sure.
But that's up to you, Jan. But so one last question: could you talk about the energy savings that could be realized from this approach? And you mentioned it briefly in the introduction, but maybe you can go into it just a little bit more. Energy savings are kind of a hot topic. So what do you get here?
Right. So based on the Pbit device, that's one thing that we compared. There we expect around like 10x energy per flip and 300x per area. But we've also looked at like at the speed computer in general, and there we have seen that we can, and we've also emulated some of this on FPGA, and there we have seen that you can get around 10 to 100x improvement just by using this emulation. And what we project that if you actually would use like this real stochastic MTJs in a large system, that you could actually get another 2 to 3 orders on top of that if you would build an ASIC based on the stochastic MTJs.
So you're talking about 4 or 5 orders in energy?
Yes, if you actually have an integrated circuit that has for example these membristors and stochastic MTJs. Yeah, all integrated together.
That's remarkable. Thank you.
So that brings us to the top of the hour. Matt, do you want to do anything to close out? Any last words?
I just wanted to thank you and all of our attendees here today on behalf of all of us here at APS. Many thanks to everyone, especially Jan and Matthew, for a stimulating discussion of this cutting edge work. Don't forget to check out our next journal club on Monday at noon, and we'll see you then. Thanks very much, everybody.
Thank you.